So second, I'd like to introduce Madelyn Cain, who is studying physics at Harvard under advisor Mikhail Lukin. She completed her practicum at Lawrence Berkeley National Lab in 2021. Madelyn, welcome.
Thank you so much for the introduction, and good afternoon, everyone. Today I'm going to be talking about how to obtain a speedup with a quantum algorithm over classical simulated annealing in solving certain combinatorial optimization problems. And as mentioned, I'm in the Lukin group at Harvard, and this group is actually half experimental, half theoretical, roughly speaking. And so today I'll be talking about both experimental signatures of the speedup as well as a theoretical understanding. So my research focuses on quantum computing, which is a type of computation that harnesses the unique properties of quantum mechanics, which come into play at microscopic length scales, in order to perform calculations. So the current challenge in the field is to develop different platforms, a few of which I show here below, that can control and manipulate many quantum bits or qubits in order to perform computations. Today, I'm going to be focusing on neutral atom quantum computers because this is an experimental research direction in our group. Here, we're storing the two states of a qubit and the two electronic states of a rubidium atom. In particular, the 0 state will be represented by an electronic ground state of an outermost electron, and the 1 state, for example, can be stored in a very highly excited electronic Rydberg state, which is what it's called. And we can perform operations on these qubits using an external laser excitation. And in particular, we can create a superposition in an atomic state where an atom exists in a linear combination of the 0 and 1 state. We can also generate entanglement or non-classical correlations between different pairs of qubits. Now, the reason that we want to do this is because many algorithms that you can run on a quantum computer are known to yield a quantum speedup over their analogs in conventional or classical computers. And to just name a few examples, this includes simulation of quantum dynamics, it includes factoring or the Fourier transform, database search, just to name a few. But the major challenge in the field right now is that running these algorithms in practice requires really fine control over a microscopic quantum system. And this is an extremely difficult engineering challenge. Nevertheless, there's been a really, I think, substantial progress in quantum hardware over the past few years. For example, in our lab, now we can perform universal low-error entangling operations on qubits. We also have all-to-all connectivity between hundreds of qubits. And so here I'm actually showing a video of individual atoms being shuttled around in the lab in order to perform entangling operations to do a circuit that prepares an entangled state of matter. And nevertheless, I would say current devices cannot yet still run large-scale quantum algorithms that I kind of have here on the left. So the question that I'll ask today is, can we still observe quantum speedup on these near-term devices? And the key idea behind this will be to focus on algorithms that have a really natural hardware-efficient implementation so that we can really access them on these devices. Today I'll be focusing on the maximum independent set problem, which is a representative example of an NP-hard combinatorial optimization problem. Here we're given a graph, and we'd like to find what's called the largest independent set, which is a subset of vertices subject to the constraint that no two vertices in the set are connected by an edge. So here I show the maximum independent set, or MIS, that we want to find in red. We'll be focusing on a class of graphs today called unit disk graphs. Here, the connectivity of the graph is decided by their layout in 2D. We're going to connect two vertices by an edge if and only if they're within some unit radius. And we'll focus on this because, as I show here, they're really naturally implemented in the hardware. So in particular, what the experimentalists will do in the lab is they will take up to 289 rubidium atoms, or qubits, and arrange them deterministically in 2D, being trapped in kind of beams of light. And the arrangement in 2D will set the graph that we're trying to find the maximum independent set of. In particular, the excited, each qubit will represent a vertex on the graph, and the excited Rydberg state will represent that vertex being in the independent set. The ground state will represent that vertex being out of the independent set. Then the natural interaction of this system, called the Rydberg interaction, will enforce the independent set constraint. What this interaction does is within some unit radius, it'll prevent simultaneous excitation of atoms into the Rydberg state. In the language of the graph that we want to solve, this is preventing two vertices connected by an edge simultaneously being in the independent set. For a certain setting of our laser drive, the many-body ground state of the system will actually encode the maximum independent set. It'll have the most atoms in the Rydberg state subject to this independent set constraint. And we are going to prepare this ground state via slow or adiabatic evolution. So the first thing that we wanted to explore was what is really determining the hardness for the quantum algorithm to solve a given graph instance. So in practice, what they'll do is they'll arrange atoms into a formation which sets the chosen graph that they want to study. They will perform an optimized quantum evolution, and then at the end of the algorithm, they will have prepared some large independent set. They'll repeat this many times to compute the probability of finding the exact MIS. This is our figure of merit. We study over 100 graph instances, and we wanted to understand what makes a graph easy or hard to solve. Theoretically, we expect that the MIS probability is determined by the adiabatic theorem, which states that there's a correspondence between the probability you see the right answer and the minimum, what's called the minimum gap between the ground and first excited state of the system. You can just think of this as the difference in energy between your lowest and your second lowest state in your system. And we can compute this minimum gap and predict it theoretically using DMRG. So here I show DMRG simulations of the gap as a function of a parameter that's changing with time. And we can exactly compute this minimum gap for each graph. We can then verify, we can look at all these graphs and we can verify that the theoretically predicted minimum gap correlates extremely strongly with the experimentally observed MIS probability, indicating that we are really verifying that this adiabatic theorem is controlling our success. There's a slight exception, of course, with a few points that really deviate from this trend. And these are instances where the experimental runtime is actually too small to resolve these minimum gaps. And for these instances, our performance is probably the most poor because when we can't resolve the minimum gap, it turns out that we can't even really optimize our evolution. And these instances are very hard for the quantum algorithm. The next thing that we wanted to do was benchmark our performance against a classical algorithm. And so we decided to focus on simulated annealing rather than a highly structured solver because simulated annealing is a very general purpose algorithm. In particular, how it works is that it stochastically updates a candidate spin configuration, which corresponds to an independent set. And each spin in particular will correspond to a vertex on the graph. How it works is it stores a candidate independent set, and it will update it to a new independent set. The update is accepted with a probability that depends both on the temperature as well as the change in independent set size. So at low temperatures, we're actually guaranteed to prepare the MIS after many updates. We then asked what controls SA time to find the MIS. And to do this, we can understand its dynamics in terms of a configuration graph. So in particular, on this graph, we take our original graph instances and we map its independent sets to the vertices of this graph. So the lighter green vertices are the suboptimal independent sets. The darker green vertices are the optimal independent sets. So these are the MIS size -1. These are the MIS. And the SA algorithm, which is the black dot, will walk along the edges of the graph until it finds the exact solution. Now, because the update is always accepted when independent sets are the same size, the dynamics among the suboptimal states will be a random walk. So you can actually prove that the SA time to find the solution is given by just the time it takes to randomly guess the exact solution, which is given by the ratio of the number of suboptimal states of size MIS -1 to the number of optimal states. And we'll call this parameter the SA hardness parameter, and it's a provable lower bound on the SA runtime. We can also prove that similar obstructions hold for a wide class of classical parallel tempering, as well as quantum Monte Carlo algorithms. We then utilize, we want to find the hardest graph instances for SA to compare against the quantum algorithm. So we generated a tensor network approach to computing various solution space properties which allowed us to predict the SA hardness parameter for a bunch of different graphs and really find the hardest ones. Furthermore, we found that the SA hardness parameter, and therefore the runtime, grows exponentially in the square root of the system size. So if you increment the system size by a little, all of a sudden the configuration graph you have to walk along to find the solution becomes a lot more complex. We then generated the top 2% instances, hardest instances using this tool, and we looked at their SA runtime as a function of the hardness parameter. And we see that, as theoretically expected, the runtime is linear in the hardness parameter. We then ran the same graphs on the quantum device, and what we see is that in red, the quantum data seems a lot more scattered. In particular, this is because, as we mentioned earlier, the quantum hardness is determined by the minimum gap, which isn't necessarily the same as the SA hardness parameter. When we look at, in particular, what we notice is that the instances where we do particularly well are the ones where we can resolve the gap and therefore optimize the algorithm. And on these instances, we see that the quantum runtime goes almost as the square root of the SA runtime, indicating that we have, on a subset of instances, a near quadratic speedup. This led us to ask, what is controlling the minimum gap? Why are we seeing such a speedup? And what is actually happening to the instances where our algorithm conversely performs very poorly? So one thing that we thought is that maybe we had discovered a hardware-efficient way to observe a Grover speedup. So Grover search is a really foundational quantum algorithm where you get a quadratic speedup over classical in unstructured search for a marked item, for instance, here in green. And for us, the marked item might be the MIS state, and the red items that we have to search among are our suboptimal states. The best classical strategy you can do here is random guessing. It takes order of the database size to do this. Whereas it turns out with Grover search, the runtime is order of the square root of the database size. And this really comes from the fact that during Grover search, you're going from a uniform, delocalized superposition of all states to your marked state, which allows you to kind of get a quadratic enhancement in the coupling between these two. However, to implement Grover search in practice, it tends to require really complex circuits. It's not very feasible to do on near-term devices. So it would be really interesting if we had discovered kind of a natural way to get this speed up. So we can actually theoretically show that an instance, given a graph instance, it will have a Grover type speedup when its lowest energy eigenstates are delocalized. So very much in analogy to Grover search, if you go from a uniform superposition of suboptimal states to a uniform superposition of optimal states, your marked state, then you will get a Grover type speedup. And we can actually predict example instances where you will have a speedup. On the other hand, we find that this condition is not met by all instances, and on some instances we can actually have a slowdown. And this explains the experimentally observed performance. So we have some instances which are delocalized. This is the darker points that get better performance, but a lot of scatter comes from instances which are localized. Last but not least, we asked the question, can we obtain a Grover speedup on instances that have poor performance due to localization? We actually answered this question in the affirmative by developing a simple modification to the traditional algorithm that we run that will obtain the Grover speedup in practice. For those that are familiar with the field, essentially what we do is we add an additional Hamiltonian term which energetically favors delocalization. And here I have some numerical verification of the speedup on the example hard instances. So the quantum runtime here is going like the square root of the SA runtime. So with that, I'd like to acknowledge many people. It's a huge collaboration. So first, the experimental team, which generated all of the experimental data that I showed today. There's a large theory team from various collaborations I've had throughout my PhD, as well as, in particular, my advisor, Misha. And last but not least, I'd really like to thank the DOE for hosting this. And it's been a really amazing 4 years getting to know everyone. And it's been an incredibly positive part about my PhD. So thank you all for listening.